All right, so let's actually do it. Let's solve this recurrence. Warning, there is a little bit of black magic here. This is not a proof I would ever expect anybody to be able to do just like off the top of their head, okay? This is something you need to have seen in order to do anything like it, okay? So you're not gonna be asked to do this from scratch today. This is pretty hard. But yeah, let's take a look at it. So I have my reoccurrence. I've written out the upper and lower. I'm going to focus on the upper though, just because it's more practical, right? It's useful to know that my algorithm will never take longer than this amount of time to run. All right, so we know the following. We know our base case and we know our recurrence. Okay, and we're going to focus right on that upper case there, so we're doing the n residual there, right, for the number of comparisons needed by the merge step. All right, so I have that. My goal, right, is to basically take C of n, right, and get it equal to something that doesn't have another C of n into it, right? That's my goal. All right, so we're going to do a whole lot of algebra here. So first thing is, I'm going to start with basically an assumption here, is I'm going to say that n looks like something that's a power of 2 number, right? So it's 1, 2, 4, 8, 16, 32, 64, 128, etc. I'm going to say it looks like a power of 2 number. And so somehow what this looks like, right, is that, like, let's say I draw a little chart here. There are 2 charts. Normally, n can look like this. It can be any number. I'm going to, just for some magic, assume that n looks like a power 2 number. So instead of looking like this continuous thing, n is like this. Well, let's see. It's going to be hard to draw. So like n is 1, n is 2, n is something like that. Only those values there look like a power 2 number count. That's what I'm going to start with my assumption. Note that this is a little bit bad because all of a sudden the stuff in between, like, so let's say this is 8, and this is 16. I'm kind of discarding 9 to 15, right? 9 to 15 could be over here, and I'm just throwing it away. I'm saying, you guys don't even exist. That could be a little problematic. Some of our assumption is going to be that whatever we come up with, right, our C value in the end, that function is continuous, right? And so if I'm sampling, right, if I'm going, every so often, right, and then allowing n to exist, right, where it looks like a power of 2 number. Well, it's like I'm capturing part of the function. It's like I'm capturing, just a sampling of it. Right? I'm not going to do every single number. I'm just doing a sampling of it. And if C is continuous, then basically, if C is continuous-ish, then it'll work out for us, right? As long as it's not too jagged anywhere, it'll be fine, right? We're just kind of restricting our domain a little bit. All right. So we're going to say n looks like a power 2. So we're saying the following. ne looks like 2 to the k. So then we're going to do, then we can basically do a substitution. Okay, so wherever there is an n in my formula, right, so I have 4 n's, I'm going to substitute in 2 to the k. So I can substitute it over here. Right, initially what it looks like is c of 2 to the k equals c of floor of 2 to the k over 2, yeah, plus c of ceiling 2k over 2, ceiling plus 2k. That's initially what it looks like, right? So that's me substituting the 2k for those 4 occurrences of n in that initial reoccurrence. So I would start doing that. Then I can actually simplify stuff. Because if I have something like, so over here, it's like I have n over 2, right, floor of that. Once I do the substitution, I can actually make it simpler, right? So it's like, okay, I substitute in here, right, and then I have 2 to the k over 2. I can simplify out that 2, so I get 2 to the k minus 1. All right, that's in a floor, but it's 2 to the k. It's not going to be a fractional number, right? It's going to be a whole. So the floor can disappear as well. So we end up just getting 2 to the k minus 1. Okay, and that's actually why we do this assumption, because we want to get rid of the floor and the ceiling, because those are annoying to work with, right? We don't want to do proofs that require us to manipulate those manually. It's just a pain. So yeah. We'll try to avoid that, right? And we did that. We're trying to avoid it by doing the substitution. And so what we get here is this final result, right? So c of 2 to the k equals 2c k minus 1 plus 2k. Basically, these two terms in the middle become the same, because once the floor and ceiling drop out, they are the same, right? That's the only difference. So yeah, this is kind of our formula now, right? So this is how c now looks. So c of 2 to the k equals to this, and this. All right, so we made these a little bit simpler for ourselves. But we're not quite done because we have c on both sides of the formula. So we still want to basically eliminate this. Now, what we're going to end up doing is we're going to eliminate the right-hand c by expansion. Let's take a look. All right, this is our initial formula here. We're going to divide it by 2 to the k, which gives us this over here. Quick note, because sometimes people get lost here. On the right hand, kind of in the right-hand side, I have this little bit here. That should be a full. Okay, so that's what it looks like that, right? 2c of k of 2 to the k minus 1. I'm dividing that by 2k. And what happens basically is that this factor here, this extra 2 factor, is going to be absorbed into this little coefficient over here. So this becomes, instead of 2 to the k, it becomes 2 to the k minus 1. Right? So this, right, is basically the same thing as right, because we have basically this extra. So this right is this on the bottom right is representing dividing by a bunch of 2's, and so on top I have a 2. So that's going to be basically divide out by that denominator. Okay, so that 2 coefficient basically vanishes into that power that's in the denominator. So yeah, that's not a spooky thing there. That's just, you know, it's just us simplifying a little bit. So yeah, then we end up with this formula over here. Okay, so this formula has my c to the 2 to the k equals c to the 2k minus 1. Done a little bit of work here. I think it's look more complicated. It's going to get worse before it gets better. We're going to basically apply that formula to itself. Because notice, this formula is a relationship between c over something and c over something, where the somethings are different by a minus 1 in the coefficient. So I can actually basically substitute in this formula into itself. So let's say I'm initially starting with this thing. I can substitute this outer thing, this whole thing, I can substitute that into here. Okay, think about that for 1 second. I'm substituting it into itself. Okay, and so look over here, notice what changes is the powers, right? So my whole expression was basically saying that c is related to this other c and the power is different by 1. If I substitute you into yourself, I'm basically reducing the power inside of you, right? So it's like I'm forcing down the power, right, in that right-hand side, right? I'm doing that substitution. Every time I do that substitution, I decrease the power by 1, okay? And notice that on the side I have a little residual, right? I leave a plus 1 behind, right? I substitute myself in, and when I do that substitution, I have both that c term and then the term that's just a 1, okay? So I'm substituting into myself. And then I do it again, and again, and again, and again, and again, and again, until I get down to this. c to 2 to the k equal c of the 2 to the 0 over 2 to the 0 plus k. Okay, and this is nice because, hey, c of 2 to the 0, that ends up just being 1. So in that case, I can go back basically and look at my initial recurrences. That basically becomes 0, right? So this kind of disappears. I have basically a little bit simpler expression. Multiply it by 2 to the k on both sides, and I get this. Okay, so a lot of stuff has happened here, right? The key thing here is that c term on the right has vanished. I only have c on the left-hand side. Now we know, right, that n is equal to 2 to the k, right? That's the substitution we did earlier. Solve it for k. Okay, it gives us log of n equal k. And then every time there's a k in here, right, all my k's, I do the substitution, revert it back, right, to n, and I get c to the n equal n log n. So yeah, there we go. So that is our analysis, right? So we started basically by writing recurrence. We picked the upper case, right, basically the worst case. This is really, it's going to be something that looks like a big O. Big O of n log n. And we did all these steps, right, to basically write this recurrence, to solve it. Right, we had to do this simplification, we had to do this expansion, this basically making the right side just disappear. And in the end, we got basically our analysis, right, n log n. So there we have it. This is our proof that the big O running time of merge sort is n log n time.